Exciting to be here in front of so many people, the wireless community, so many startups. My background is not in agriculture. I grew up in India. My PhD is in computer science. I joined Microsoft in 2005. I joined Microsoft Research, where I've been doing different projects, a lot of them on networking. And then around 2015, I started this project. It was kind of like a startup within Microsoft, where I started this project. And then in 2018, I moved into the Azure team as the chief scientist of Azure Global. And we announced our product last year in November. I'll tell you more about that. But that said, my background, as I said, is not in agriculture, but I did grow up in a farm in India. That's my grandparents used to live in this farm. And as it happens in India, I see a few Indians here, you spend a lot of time with your grandparents. So every summer and winter vacation, that was 4 months every year, we were 3 brothers and a sister, all of us would go to that farm. Back then, I hated anything to do with agriculture. I did not look forward to spending time in that farm with my grandparents because these farms did not have any electricity. They didn't have any toilets. And by the way, a lot of farms in India are still similar. So I didn't look forward to those 4 months every year. But that said, it did give me enough exposure that this is the project that I wanted to work on. And that's what triggered the start of this project, FarmBeats. So the goal of this project is to help solve the world's food problem. That is, the world's food production needs to increase by 70% by 2050 compared to 2010 levels to feed the growing population of the world. And it's not just about feeding people. We need to give them good food, nutritious food. And we need to get to this increased food production without harming the environment. The amount of arable land is not increasing. The water levels are going down. The soil's not getting any richer. So how do you get to this increased food production in a responsible way? The most promising approach to solve this is that of data-driven agriculture. That is, if you could get large amounts of data from the farm and use that to drive some of the agricultural decisions, it can help address some of these world food problems. For example, what you could do is, if you had a farm like this, and you could get large amounts of data from the farm to build maps like this. For example, what is the soil moisture map 6 inches below the soil throughout the farm? If you could build maps like this, it would enable techniques like precision agriculture. That is, you could then apply water only where it is needed, when it is needed. You could apply pesticide only where it is needed, nutrients only where it is needed. And precision agriculture as a technique has been shown to improve yields. That is, you can take care of plants better. It has been shown to reduce cost because you use less water, less pesticide, less nutrients. It's also better for the environment for the same reason. You're not wasting water, you're not wasting pesticide. Once we started showing these capabilities to build maps like this, we were approached by some of the seed companies. They wanted to use this for a new technology called phenotyping. That is, just like you could phenotype humans, you can phenotype plants. That is, they wanted to understand why did the same seed variety grow differently in different parts of the farm, in the red versus the yellow versus the green parts of the farm. If you could understand that, you can realize a future where you could, instead of putting the same seed throughout in the farm, a farmer would go buy different bags of seeds, plug in this map, and based on what the farm looks like, you could put in different seeds in different parts of the farm. So there's precision agriculture, there's phenotyping. In fact, there are many other applications of data-driven farming as well. The thing is, precision agriculture as a technique was proposed back in the 80s. It still hasn't taken off. And the biggest reason it hasn't taken off is the cost of existing data-driven agriculture solutions. Just to give you an idea, I was at UC Davis. There was an expo going on there. There were lots of companies presenting the latest and greatest precision ag equipment. And the cheapest package was 5 sensors for $8,000 and a recurring cost. So this has been the biggest limitation of agriculture. That is, even if you put 5 sensors, it will only tell you what's happening at that location, not what's happening 10 meters away. So that has limited the adoption of precision agriculture or data-driven agriculture, even though the benefits are well known. And that is the goal of the FarmBeats project. And I know many of you here can relate to this goal, given that you're working on LoRaWAN technologies, which itself has that goal of bringing down the cost of these solutions significantly. So FarmBeats helps address some of these problems by solving some of the problems around connectivity, power. You can relate to some of the things that were discussed in the previous talk as well, around edge computing, as well as the number of sensors that are needed. And I'll briefly touch upon each of these solutions as well. So the first challenge is that of farm connectivity. That is I'm mostly talking of big farms like the ones in the US and Canada. The farmer's house has some sort of connectivity to the internet, but the farm is a few miles away. Even though sometimes connectivity might exist when you plant the seeds, by the time the crops grow, the connectivity is lost. The question then is, if you do not have any connectivity in this field, how will you get data, not just from sensors, but from drones, tractors, cameras? How will you get all of this data to the farmer's house? To address this problem, we use a prior research that I have been working on since 2005 called the TV white spaces. What the TV white spaces enables is, imagine if you had a Wi-Fi router and you could access it a few miles away. That would be cool, right? And the way we do that is we took a Wi-Fi signal and we put it in empty TV channels. This is TV you watch using over-the-air antennas. You know, when you browse through TV, on certain channels you see a transmission. On the other channels, all you see is white noise. Back in the day, this was about 10 years back, we had developed this technology where you could take a Wi-Fi signal and put it in these noisy TV channels in a way that doesn't interfere with your TV reception in an adjacent channel. So you could be watching channel 7 at home. On channel 8, we could be sending Wi-Fi signals. And here, when I'm talking of TV channels, they are in VHF and lower UHF channels. That is, imagine 170 megahertz to 220 megahertz, or around 470 to 600 megahertz of spectrum. Compared to even if you move LoRa, which is a 900 megahertz down to VHF bands, it's the same protocol, LoRaWAN protocol in the lower bands, you're talking of about 4 times the coverage and much better propagation through trees, crops, canopies, and so on. So back in the day when we had developed this technology, we had the FCC chairman who had come to see the demo we had put together. This is made legal in the US, Canada, UK, and quite a few other countries worldwide. So just to give you an overview of how this technology works, just in one slide, I'm covering 5 years of my research. So I'll just cover it at a very high level, but it'll give you an understanding of how this technology works. So any device that has this TV white space radio, what it has to do, it has to scan the spectrum. So the x-axis here is frequency, the y-axis is power. Every red bar is a TV channel. So every device would first scan, figure out what are the TV channels that are being used in the area. It would then start operating in these empty TV channels, which are known as the white spaces. While it is operating there, it will keep continuing to listen to see if a TV transmitter came back. If it did, it's going to move to another part of the TV spectrum. And if needed, it's going to adjust its power level or its bandwidth. So these are the different things that distinguish it from, say, an existing Wi-Fi or a cellular radio. Underlying it, the protocols could still be the same. So for example, one of the things we've done is we've taken one of these Semtech radios, and what we did is we built this module, which is a triple band module. It does both LoRa, that is, you could be operating in 800 or 900 megahertz of the spectrum, or you could move to UHF TV or to the VHF TV channels. The benefits you're getting is, depending on the thickness of the crop cover or canopy, you could dynamically move to different parts of the spectrum and get much better propagation, depending on where you're operating. So as I said, this technology became legal in the US in 2010, in UK a couple of years later. At Microsoft, we've been pushing this technology further and further. And one initiative we launched, this was in 2017, is called the Airband Initiative. As part of this initiative, Microsoft has made a pledge to connect 3 million rural Americans by 2022. And to do this, one of the key enabling technologies is the TV white spaces. That is, we are creating partnerships, we are investing in companies, we are actually going and helping them out to establish this infrastructure to connect more and more of the rural population to the internet, to broadband internet using this technology. The key intuition, by the way, in the context of agriculture was that TV towers are where people are. You'll have TV towers in DC, in Amsterdam, in the big cities. The farms are usually away from the cities. So if you turn on a TV in the middle of a farm, most of the channels will be just white noise. In fact, even if 20 TV channels are available, and I'm being conservative here, I was giving this talk at the National Corn Growers Convention in the US, and a lady actually lifted her hand and she said, 20, I hardly get 2 TV channels in my house. So in the farm. So the more empty TV channels there are, the more unused capacity there is. That is, each TV channel in the US is 6 megahertz wide. Here, it is 8 megahertz wide in Europe. Even if 20 TV channels are available, we are talking of 20 times 6, 120 megahertz of available spectrum. What that means is, usually for capacity, multiply that by 3.6 typically. So we are talking of close to 400 megabits per second of available capacity using this technology. And our vision here is just like Wi-Fi connects your house, the TV white spaces can be used to connect your entire farm, getting data from cameras, drones, tractors. So while we did this for broadband devices, and what you're seeing on your left is a broadband device that is FCC certified, right now what we did is we use the same thing with LoRaWAN as well. That is, either we could use existing LoRaWAN devices, or wherever possible, you could move it to these lower frequencies. Imagine VHF spectrum, right, 150 megahertz. You suddenly start getting a lot more coverage using these radios. So with this TV white spaces technology, you can see how you can start bringing broadband to these unconnected areas. The second challenge is, if you had to build a map of a farm, say, what is the soil moisture level 6 inches below the soil throughout the farm? If you had to build an accurate map, you would need lots and lots of sensors, say a sensor every 10 meters, because the soil moisture varies from row to row. But putting a sensor every 10 meters is going to be expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So the question we asked was the last bullet on this slide. That is, can we build a map using very few sensors in the farm? To solve this problem, our key insight was to use drones. These are UAVs that have a camera at the bottom, and they can cover large areas very quickly, and they come for about $1,000. And what we did then was we came up with a technique where we use aerial imagery to interpolate the data from a few sensors to start building these maps of the farm. So we are using AI and machine learning, and we incorporate 2 key insights as part of this. That is, if 2 sensors are close to each other, 2 points in the farm are close to each other, they are likely to have similar values. And the second insight, which we call visual similarity, that is, if 2 parts of the farm look similar, not just in RGB, but in multispectral or hyperspectral imagery, they are likely to have similar values. And we incorporated both of these insights in a machine learning model. These are 2 different kernel functions running at the same time to start making these interpolations. So the way the system works is, if you have a farm, we have a sensor placement algorithm. You'll strategically place sensors in the places that it's needed, and then you get an aerial image, either from drones, or now what we've done is also with satellites. You can then interpolate it to start building these heat maps of farms at a resolution that wasn't possible before. For example, here, what we've done is, you take the sensor data, you then combine the data, either from drones or from satellites, you merge these to start building these kind of maps. And we've written a paper where we did this interpolation for soil temperature, soil moisture, and soil pH. And in the paper, we showed that compared to existing schemes, which use linear interpolation or Craiging's method, using aerial imagery can give you 3 times more accurate maps than existed before. So the third challenge, I talked about TV white spaces, which can provide connectivity at lower cost. I talked about how you would need much fewer sensors than otherwise needed to build maps like this. The third key problem is that even though with the TV white spaces, you can get large amounts of data from cameras, from drones, from tractors to this farmer's house, the connectivity from the farmer's house to the cloud is weak. Most farmers pay for broadband, but all they get is 1 to 3 megabits per second connection. And every time you fly a drone, you're getting close to, say, 2 to 3 gigabytes per 15-minute drone flight. So if you cannot send these drone videos to the cloud, how will you get the benefits of the cloud of the AI machine learning to a grower, to a farmer? To solve this problem, our key insight was that most farmers have PCs. If they don't have a PC, we ship them a PC form factor device running Azure IoT Edge. This thing sits in the farmer's house or office and does a lot of compute sitting in the farmer's house or office, doing a lot of AI, machine learning, computer vision, and such that it can even operate offline when the farmer doesn't have any internet connectivity. Just to double-click a little bit on what's running on the PC, everything you're seeing in this big gray box is what's running on the PC. It gets data from sensors. So on this PC, on the USB drive, you would put, say, a USB LoRaWAN gateway, which could start getting data from sensors. You'd get data from drones using the TV whitespaces receiver. You could get data from cameras. And all of that is ingested on this PC device. Then this data then flows into the processing component where we are doing orthomosaicing, 3D point clouds of the drone videos. We generate the heat maps, which then flows into the last column here, where we are running these precision ag services on the edge as well. These services are not something that Microsoft's going to build. This is something where we work with partners who would build these services. Each of these are running in containers. What that means is you could easily move it from the edge device to the cloud, wherever this compute is to be run. So I won't dig much deeper into this, but if you have questions, I'm available today and happy to answer any questions about this slide. So power, I didn't mention much about power, but we are doing some interesting things there as well. So just to extend some of the ideas from the previous speaker, what we are looking at, this is research going on with the University of Washington, is if you have a transmitter, high-power transmitter, say a TV whitespaces transmitter in the farm, can you use RF power to start powering these sensors? At which point, can you make these sensors battery-less, right? Just using these, the harvested RF power. That's still in active research. One of the other things which we did, which I really like, is we built this. There was an intern of mine from Purdue University. He spent the summer in 2015 with me. He came up with this really cool idea to improve the battery life of drones. So if any of you have used drones, you know that one of the biggest limitations is battery life. It will last, say, 25 to 30 minutes on a single flight, most of these commercial drones. To make them last longer, the interesting idea that he came up with was to use wind to improve the battery life. That is, you know, when you're sailing, using a sailboat, you change the direction of your sails based on wind. When you're skiing, you change the direction of your ski to accelerate or decelerate. You could do the same thing with drones. Once your drone is in flight, you could change the yaw of the drone to use the wind to accelerate and decelerate. And what we showed was that when wind was between 5 and 15 miles an hour, we got up to 30% improvement in drone battery life. So these are some of the things that we are continuing to innovate on. That doesn't solve the problem, but takes it a step further. So we've done several deployments of this technology, even when it was in research, from farms as small as smallholder farms in Africa and India to the big farms in the US. Some of the ways in which the farmers are using it is, one thing we built on top of this is microclimate prediction. That is, once you put in a sensor in the ground, say for measuring soil moisture, we are not just telling the farmer that, hey, this is the soil moisture right now. We are merging this data with the weather station data to start making predictions of what will the soil moisture be up to 5 days in advance. So the way we built this model is we took data from 50 different weather stations across Washington state over the last 7 years at 15-minute intervals. We used that to train a model, and then when you plug in a new sensor, we do transfer learning to then transfer that model to the sensor that's in that farm to start making very hyper-local predictions of what's happening in that farm. So as you know, weather is one of the important parameters in agriculture, and a lot of farmers right now, they rely on the weather that the weather stations are providing, not really what's happening in the farm. With this, we can start making very hyper-local predictions. For example, here what you're seeing in this graph is for soil moisture and soil temperature. As you can see, even up to 5 days in advance, if you look at the red bar, the error is less than 10%. And here is a testimonial on your bottom left by a farmer that's using this. So he wanted to spray the farm. The weather stations, the weather prediction told him that the temperature is going to be 40, I think it was 42 degrees. We told him it was going to be 31, it ended up being 30. If he would have sprayed herbicide, he would have killed his crop if he had done it at that time. This is another use case. This is a farmer in upstate New York where he wanted to know how his cows were doing when his cows were out in pasture. This is a 4-kilometer stretch. We flew the drone, transmitted the data over the white spaces to an edge device in the farmer's house. And within 30 minutes, we could start flagging things like the grass is growing back well from left to right. There is a water puddle that needs to be fixed before the next planting season. The cows are pooping well, which is also important information for the farmer. This is for machine learning enthusiasts out there. This is deep learning on cow poop. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is a farm near Microsoft campus, about 25 miles east of Microsoft campus. This is a small farm, around half an acre. We do a lot of demos on this farm. So if you all are in the Seattle area, especially in the summer, do let me know. Would love to take you to this farm. Bill Gates was here in 2018. He wrote a blog on this on Gates Notes as well. We do a lot of demos on this farm. We show the farmer these beautiful pictures. We overlay this with data. For example, we put these sensors, some of them connected via LoRaWAN, some LoRaWAN over TV white spaces. We fly drones, use satellite imagery, and we show these maps. This is a soil moisture map. We were able to flag that the bottom left part of the farm was moist, even though we did not have a sensor over there. This is a pH map. After the farmer had applied lime, we are able to flag that the dark parts of the farm are still acidic. The farmer needs to reapply lime before planting the seeds. This is another farm in upstate New York. We have 3 cameras streaming data to this edge device where we are seeing how the cows are moving, whether a cow is sick, and so on. So as I was saying, this was all in research, and then in 2018, I moved to the product side. And in November last year, we announced our product. This product is the Azure FarmBeats product. It's available on Azure Marketplace. You can, if you're using Azure, you can go to Azure Marketplace and install this for free. What this does is it would install 2 key components in the cloud. So in this figure, everything in yellow is built by partners. Everything in green is what we are building with as part of Azure FarmBeats. And everything in blue is what is available on Azure. So as you can see, things we are providing are data hub, TV white spaces, the accelerator, and so on. What this does is once you install FarmBeats in your resource group, by the way, this is not running in Microsoft's subscription, this is running in your subscription. Once you install it, you can then create a farm here, I mean a plot, which is essentially a polygon or a shapefile. Once you create that polygon, you can then start attaching sensors to it, drone partners, satellite partners, weather partners to it. And you can then start seeing all of this data corresponding to your farm in one place. And we have all the things in yellow are built by partners. And these are partner companies that we work with. For example, on the sensor side, we have Pessel Instruments as one of the partners. We have Davis Instruments. We have Teralytic. We are also working with Seed, who has a booth here as well. On the drone side, we announced partnerships with DJI, with SenseFly, Parrot, with EarthSense, which builds a robot, and so on. And we are creating partnerships on the weather side with DTN, and so on as well. So once you create this data hub, you can create your farm, you can link in all of these, and everything will be available in one place. FarmBeats also comes with a solution accelerator. This involves code to do device management, it has a sample web dashboard as well. You can visit the Microsoft booth here to see that sample dashboard. It also comes with some AI and machine learning algorithms, like, for example, the soil moisture model I talked about, where if you put a few sensors in the ground, it combines it with aerial imagery, with satellite imagery or drone imagery to build out these maps of your farm. So you'll start seeing that on this dashboard as well. The way this goes to the growers is at Microsoft, we realize that we are not an agriculture company. We don't have the expertise nor the sales force to sell to the growers. The way we are going to the growers is via the big companies or through ISVs and partners. These are companies that have, or existing organizations or groups, who have a touch point with the farmer. And we are enabling them with the power of the cloud, with the power of IoT, bringing LoRaWAN, bringing all of these other data streams to these agricultural companies, helping them achieve their digital transformation. So I talked a little bit about the research that we are doing. There's quite a bit of work going on there, including some latest work we've done on using Wi-Fi signals to start measuring soil moisture and soil EC. I talked a little bit about the products that we are building in this space. At Microsoft, we are taking it all the way, by the way, as far as societal impact goes. Even though we are not selling to the grower, we are making investments that it gets there. One of the initiatives I wanted to talk about is via the Tech Spark initiative. What we've done is we are working with the FFA, which is the Future Farmers of America. And what we built is a FarmBeats student kit, which we are giving out to these high schools. So we actually held a competition, 400 high schools in which these farmers go. They applied to this. We picked 50 of them as winners, and to each one of them, we gave 2 FarmBeats student kits. And last summer, we had a hackathon for the teachers. We had teachers on campus so that we were hacking on the curriculum. And the goal here is to make these farmers realize the power of data and data-driven agriculture early, even when they are in school. That is one of the big problems that you see in agriculture these days, is that the next generation of farmers don't want to do farming. And this is not just in the US, this is a worldwide phenomenon. Even in places like India and Africa, even the village I was talking to you about, where I spent a lot of time, most of the people around my age in the village are no longer in the village. They are all going to cities. Even though they won't make as much, they are getting away from agriculture. Our goal here through all of these is to make agriculture cool again by showing them the benefits of how technology can help farming, help address some of those key problems. And in fact, one of the things the next video I'll show is from this farmer. There is a farmer we work with in Eastern Washington. He had a similar thing. He went to University of Washington, studied computer science, took up a tech job, and then went back to agriculture to start using tech for farming. This is his story.
Eastern Washington's my home. I describe it as one of the most beautiful places on earth. My father farmed this land before me, and before him it was his dad, and his dad before that. I'm a 5th generation farmer, and so I do have a very close connection to the land here. Farmers need a lot of tools to make better decisions. Any decision on a farm is really a big deal. Azure FarmBeats combines information from IoT devices, insights from machine learning, and serves it up in a way where other platforms are able to build off of it and help make a farmer more productive. The sensors measure temperature, wind, rain, humidity, soil moisture and soil temperature, CO2 levels, the solar intensity as well. One of the ways that the model can help make better decisions is temperature predictions. So that model will then tell you, oh, it's going to freeze tomorrow morning, and it's going to freeze, in the lower area. The whole field is not the same. So this year, when I have multiple sensors in one field, what I noticed was the soil profile on the top of the hill was different than on the bottom of the hill. And usually what we do is we plant the whole field the same, but it was so different that I seeded fewer plants up higher in the field and seeded more down lower. And then I could track it throughout the year with drone flights and with yield data at the end of the year. The big surprise is I didn't think it looked as good, but when I harvested it, the data allowed me to get a much higher yield than I was expecting. It's a very counterintuitive idea that you have fewer plants and yet they produce not just more, but they were producing twice as much. It's just the first year, but if I can do this every year, that's something that's really going to help our farm a lot. The way my dad used to farm and figure out what was going on in every field was he would walk through the field. So being able to know, what the soil moisture is like at a field that's 20 miles away is very beneficial to me. Family time for me is very important. I have 2 little kids, 2 little boys. Being able to save that time allowed me to spend more time with my family. I love being a farmer. I wish that it were easier sometimes, but that's why I harness every tool available to make it easier and make it something where I can continue farming.
Yeah, so to conclude, so Azure FarmBeats is we bring in tools to acquire large amounts of data from the farm and then merge all of these data streams, for example, from sensors, satellite drones, to then start enabling these kind of scenarios that benefited Andrew. If you want to learn more, we would love to partner with you all. You all here I see as potential partners. They're some of our existing partners here and would love to tell their stories as well. So do reach out either directly or you can ping me at Ranveer@Microsoft.com. Would love to talk more. Thank you.
Well, thank you very much, Ranveer, Chandra, for actually making farming more fun for us techies. Time's up. I have a short question for before you go.
Yeah.
Who owns the data? Is it the farmer? Is it Azure? Or is there also a lot of open data we can do our data analysis with?
Yeah, this is a very good question, and data ownership by itself is a very hard problem. Is it the farmer? Is it the farming company? One thing we know is Microsoft's not owning that data. So from our perspective, FarmBeats runs in the customer subscription, and we rely on the agreement between the farmer and the farming company about who owns the data. What we are doing is we are providing the mechanisms to make sure, for example, at the edge, you can decide whether which cloud this data goes to or whether it leaves the farm at all. So we are providing the mechanisms, but it's open to debate who should have the data or who should be benefiting from the data. I think all of us should be benefiting without hurting the farmer in any way.
For further questions, you're around, right?
Yeah.
Okay, thank you very much. Ranveer, Chandra.
Thanks.